This is Inorganic Chemistry, Chapter 4, The Structures of Simple Solids. We will cover 8 sections in this chapter. Sections 1, 2, 9, 10, 11, 18, 19, and 20. Section 4.1. Unit cells and the description of crystal structures. We will review 3 unit cells first: simple cubic, body-centered cubic, and face-centered cubic, by watching this video. You can click this link or click here. This 28-minute video introduces the 3 cubic cells and also tells you how we come up with these numbers for the 3 structures: the number of atoms, the coordination numbers, the silence of the cube, and the packing efficiency. So in the end, the face-centered cubic structure has the highest packing efficiency. Be sure to watch this video. Now let's look at unit cells. So imagine this is a 2-dimensional crystal structure, and this is a unit cell. So if you do a translation of this cell, so to here, and then in this direction, and then in this direction. So if you repeat this unit cell many times, you will get a 2-dimensional crystalline structure. However, this is not a preferred unit cell. Why? This is too big. This is not the smallest unit cell. Over here, this is actually the smallest unit cell. Again, you can do a translation. You can do the translation to the left, and you get the same unit cell here, and you can move it up to here, and you can move it to here. So if you repeat this unit cell in X and Y directions, you will also form the same crystalline structure. And this unit cell is smaller than this unit cell. So let's count. In this unit cell, you have 1 orange. And then you have 4 times a quarter of the green atoms. So you have 1 orange and 1 green. Over here, I think you have 2 greens. So you have 1 green here. And each of the 4 corner atoms contributes only a quarter of the atoms. So you have 2 greens in total, and then 2 orange in total. So both are unit cells, but this one is the smallest unit cell. Therefore, it's preferred. This one is not a unit cell because if you look at this, supposedly if it's a unit cell and then you draw another one, and then you can see over here, top left corner, you have orange. But then you look at this one, top left corner, you have a green. So that's different. These 2 unit cells are different. You can't just do translation of this unit cell to form the entire crystalline structure. So again, these 2 are legitimate unit cells. This one is preferred because this one is the smallest unit cell. Now let's look at the 7 crystal systems. You have learned this cubic structure. You may have A equals B equals C. Those are the silence. They are exactly the same. This A, B, C are also called lattice constants. And then you have the angles alpha, beta, and gamma to be 90 degrees. And then there are 6 other different systems: triclinic, monoclinic, orthorhombic, rhombohedral, tetragonal, and hexagonal. So all those, you have different lattice parameters or lattice constants and different angles here. So now let's look at the pictures of the 7 different crystal systems. All right, those are the 7 crystal systems. All crystal structures belong to one of the 7 crystal systems. So let's look at the cubic structure first. So look at the 3 silence. They are exactly the same. A is equal to B is equal to C. So the silence are exactly the same. And also, if you look at the angles, they're all 90 degrees. Tetragonal, okay, you have A by A, so this is a square, but the height is different. It's C. How about the angles? The angles are 90 degrees, 90 degrees, and 90 degrees. So one angle here, 90. This one, 90. And then on the bottom, it's also 90. Same here, all three 90 degrees. However, the three edges are different. A, B, and C are all different. Now over here, you have monoclinic. So you have this 90 degrees, this 90 degrees. However, this beta is different from 90 degrees. All right. Also, this one is different from 90 degrees. And then you look at the three edges, A, B, and C. They are different. Triclinic. Not only A, B, C are different, but the three angles are different. You have alpha, beta, and gamma. They're all different from 90 degrees. So over here, this is rhombohedral. So this one is actually fairly symmetrical. So if you look at the three lengths, A, and A. So the three lattice constants are exactly the same. And about the angles, they're also exactly the same. This is a rhombohedral structure. Finally, hexagonal. Hexagonal structure has, look at this, hexagon on the bottom with a silence of A. So this A. And then the height is different. It's a C, okay? It's a C. C is different from A. And then if we look at the angles, we have 90 degrees here. We have 90 degrees here. So 90, 90. But then on the bottom, you have 120 degrees here. Or if you look at this, 120, 120, 120, 120, 120 degrees. This is the hexagonal structure. So again, all solid crystals belong to one of the 7 crystal systems. This 7 crystal systems, depending on whether we have other atoms on the surface, on the faces, or in the center of the unit cell, we can form 14 Bravais lattice. All right, so we have cubic crystal system. And then we have primitive cubic or simple cubic. So this is primitive or simple cubic. But also we can have body-centered, we can have face-centered. So for the cubic crystal system, we have 3 Bravais lattice. For the tetragonal crystal system, we have 2 different Bravais lattice. So this one is simple, this one has this body-centered. And then this is orthorhombic. And then we can have, this is called base-centered, body-centered, and face-centered. Again, this is base-centered. Rhombohedral. And then over here, monoclinic. Again, those are base centers. Triclinic. So again, in total, there are 14 Bravais lattice. And you can look at this webpage to get more detail about this 14 Bravais lattice. Now let's look at the definition of the lattice points. So if you look at this simple cubic, there are actually 8 lattice points over here. This O stands for origin. So this is origin. It's 0, 0, 0. And let's say this is x direction. And then it's just 1, 0, 0. This one means you have 1A, 0B, and 0C. So now how about here? It's going to be just 0, 1, 0. That means 0A, 1B, 0C. How about this one? This one is 0, 0, 1. Okay, 0, 0, 1 means 0A, 0B, 1C. How about this one? You get 1B and 1C. How about this one? You have 1B, 1A, and 1C. So this lattice point has a coordinate of 1, 1, 1. So again, 0, 0, 0, 1, 1, 1. This is 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1. Okay, this guy, 1, 1, 0. How about this one? 1, 0, 1. All right? In the body-centered structure, you have a lattice point. In the middle, it's half, half, half. And now, face-centered, you have 6 atoms sitting on the center of the 6 faces. And then what you can see is, if you look at this lattice point, the coordinate is actually half A, 0B, and I'm sorry, I think this is half A, half B, and 0C. So it's supposed to be half, half, and 0. All right? And then you can look at this one as well. So this one, 0A, half B, half C. So the coordinates are 0, half, and half. All right. And similarly, you can look at this one. I think if you look at this one, you have half A, you have half B, and 1 C. So the coordinates of this lattice point is half, half, 1. All right. Now, if we have ionic compounds, just look at one of the two ions. Okay, don't look at both ions. So in this case, this is zinc sulfide. All right, the bigger green ones are the sulfide ions. Just look at those green ones. And then this is so-called face-centered cubic. If you look at this zinc 2+, they just occupy the space. For example, between 1, 2, 3, 4. This 4 sulfide, okay, form a trigonal pyramid structure or tetrahedral structure, and at the center there's a little bit space, okay, interstitial space, and then this small zinc 2+ ion can utilize this very small space. This zinc 2+ sits in the center of this between this 4 sulfide ions, and this one, again, 1, 2, 3, 4 sulfide ions can have a little bit of space in the center occupied by this zinc 2+. So that's why this is this face-centered cubic structure by not looking at the zinc 2+. Same here. So you need to focus just on the chlorine minus, and then you can decide it's a primitive cubic structure. This cesium plus forms 8 bonds with the 8 chloride on the corners. We can also do a 2-dimensional projection of a 3-dimensional crystalline structure. For example, if we look at this structure, we can just draw a 2-dimensional structure. For example, this is just the top view. However, if you look at this from the top, look at this center atom. This center atom has a different coordinates in the z direction, right, than this layer or this layer. So somehow we just need to specify the coordinates of this atom in the vertical axis. It's half C, so you see this half here. And then if you look at this atom and this atom, if you draw a 2-dimensional picture of this unit cell from the top view, these two have exactly same coordinates for the x and y direction, but different z direction. So in the z direction, this one is 0C and this one is 1C, so we have 0 and 1 here. Now, what about a face-centered cubic structure? All right, so again, we'll just do a 2-dimensional picture here. You know, this is just the top view. But if you see 0 and 1, that means there are 2 layers of such atoms. All right, so with a height of 0C and 1C. And then what about the atoms on the faces? So the height is half C here. So this one is, 0 and 1C. All right, so again, those numbers are simply telling you what are the coordinates of these atoms in the 3rd dimension, okay, perpendicular to this screen. One more example. This is a little bit complicated. This is silicon disulfide. So right now you're looking at a 2-dimensional projection, and with this labels of their height. So again, 0 and 1 means you have 2 layers of such atoms. All right, and then this means the height of the silicon atoms is just 1/4 of C. In a direction perpendicular to the computer screen. So maybe it's better to just look at this 3-dimensional structures as well to better understand this picture. All right, this is the silicon sulfide over here, and you can look at this 2-dimensional structure, and you can click this spin, and you can see the 3-dimensional structure. And you can see the two silicon atoms with a height of 1/4 of c. And I think you can show or hide the H, and then you can zoom in. All right. All right, get back to this. Again, I encourage you to use this website, CamTube 3D, to look at the three-dimensional structure of this 2D projection.